Welcome everyone to the Palmer Museum of Art. And our lecture today is part of the Entangled Conversations lecture series, which is associated with the exhibition entitled Plastic Entanglements, Ecology, Aesthetics, Materials, that runs through June of 2018. Among our distinguished lecturers today is another one of our own faculty members here at Penn State, Dr. Melik Demirel, who is Director of Craft Center. He's also a member of the Materials Research Institute of Engineering, Science, and Mechanics, and of the Huck Institutes of Life Sciences here at Penn State. He has a really interesting career in engineering new materials, and he will be speaking about that today. The title of his lecture is, "What is the primary driver of plastic pollution? Technology, society, or state?" Please welcome Melik Demirel.
Thank you, Jennifer, for inviting me to give this talk today. I'm very excited to talk about the primary drivers of plastic pollution. I am the director of the newly formed Craft Center at Penn State. And today I'm going to talk about the textile aspects of the plastic pollution. So, plastics in textiles. As you can see from the chart, 16 million tons of plastic textile is being trashed every year. And 65% correspond to landfill, 16% goes to the combustion, and 19% goes to the recycling. So if we can even extend the time period for lifetime for plastics, textiles by 3 months, that corresponds to 5 to 10% of reduction of carbon footprint. So as you can see, this is a very important problem. So where does it come from? At the beginning of the century, we invented different kind of plastics that replaces natural fibers like silk, wool, and cotton. Nylon was the first replacement that came in 1930s, and polyester and acrylic followed that. And since then, specialty fibers has been produced. Although we have been enjoying these new fibers, recently we realized that these fibers are creating microfibers that are not detected in the waste streams, in the washing machines and in the waste treatments places, and they are creating pollutions in the water. So let's go back to the history of natural fibers. Since the dawn of the civilization, we have been producing different kind of natural fibers. These are cotton, silk, wool, remi, shishel, and hemp. So these have been used for the last thousands of years, but we have changed the use of these plastics and moved into synthetics. We have to ask the question why. As you can see from this graph, which is basically plotted in logarithmic scale, you can see the time from years and the population, the corresponding population. What you see is a major 4 jumps in the graph. The first one started early 70,000 years ago on cognitive revolution, where the population was just lower than 1 million. And since then, the agricultural revolution moved the population drastically to tens of millions, and the concept of writing, and finally the scientific and industrial revolutions change the population of the earth. So if you look at the problem from the perspective of population, we see that the increase in technology is feeding into food, and the increase in the food production is feeding into the population. And this cycle keeps going and going and again, which increases the population. But let's look at the brief history of the plastics. So before the invention of the plastics, there were clays and glass, but they were brittle. There were some natural rubber, which is a moldable and thermoplastic material that came from the trees, were around, but it was in limited resources. Charles Goodyear, in 1939, he started working in the synthetic rubber, and he had shown the first time that you could use synthetic methods to make rubber in the laboratory. And the Goodyear took this technology after his death and commercialized, as you know it today, the tires of the cars. The first plastic came in 1907 with bakelite, and then the PVC became the construction plastics. Polystyrene and PMMA used in household goods and in the cars, and finally the silk replacement, the nylon, come to the picture. And most recently we have the PET, which is basically the plastic bottles. Obviously, we shouldn't underestimate the efforts in this direction. Nobel laureate since then has been awarded in the areas of macromolecular chemistry, polymerization techniques, physical chemistries, polymer properties, and finally conductive polymers. So from the previous slides, we know that the population increases as we increase more food, and the food and the population feeds into technology again. But this creates a huge stress in nature and ecology. Although the human populations are increasing, the number of other species are under stress because of the ecological and environmental disasters due to the humans. So this problem has been studied in the last 100 years or so by different philosophers, including Heidegger, Marcuse, and Habermas, which addresses the commodification problems in the technological domain. So what can we do about the technology from that perspective is a key question that we need to address. But let's look at some of the fundamental properties that we have seen we can compare with the synthetics and natural materials. As you see in this plot, we shown the Young modulus, which is an elastic property of a material, versus the strength, which is another mechanical properties. And these are two graphs that compares engineering materials that are man-made and natural materials that are from natural sources. As you can see, there is one-to-one match in most of the areas, and from bricks to polymers to foams to composites, there is exactly same mechanical properties equivalent in the natural domain, from soft tissues to mineralized tissues to natural fibers and wood-like materials. The reason that we switch into man-made materials are because of the higher cost and lower abundance. And the higher cost is not the real cost to the environment, but it's the real cost to the market. So although we are ignoring the cost of the production here, the environmental effects are not included. So let's look at the problem from the beginning. Cost versus sustainability. Due to exploitation of natural resources and cost issues, plastic replaced bio-derived materials in many industrial products. So oil turned into plastic, plastic turned into another disaster. So this environmental pollution is creating a sustainability issue. Let's look at the natural building blocks. So nature uses different types of blocks, from glycans to lipids to natural amino acid and nucleotides, to create what we have. Whatever you see around you, all the living things are made of these four building blocks. And precisely, if you look at natural polymers, what we see is they are highly repetitive structures that are common in resilin, which is the insect wings, elastin, which is in your skin, silk is the spider or the cocoon, collagen, part of your tissues, keratin, part of your hair and nails. So recently we invented a new plastic from another natural source. Squid ring teeth comes from the tentacles of the squids, which are tiny little rings that are embedded in the suction cups. that helps the squid to grasp the prey when it is attacking. So what we have done is we collect different squid species around the world and start analyzing these samples. By looking at the genetics of the squid's ring teeth, we have designed new organisms that can produce the same material in the bacteria and yeast. Using the standard biotechnology methods, now we can make powder, polymer, and liquid solutions of these materials. So basically, we were able to take different types of squid genome and that can create the ring teeth, and we're able to make repetitive polymers that can be produced in the bacteria. In this slide, you can see the biofermentation process done in my lab. In this slide, you can see this self-healing plastic behavior. In this presentation, you can see our efforts of self-healing textiles. So the critical use of this material could be shown for microfiber applications as in this figure. So any microfiber, for example a micro rag that is shown in here, can be coated by our squid material, squid ring teeth material, which enhances its wear and tear resistance. As you can see, electron microscope images here shows that after wear and tear, the uncoated samples can be damaged easily. But on the other hand, on the lower case, you can see that coated samples will increase the integrity. The squid ring teeth coated samples will increase the integrity, therefore minimize the microfiber pollution. So then the key question is, why don't we have these materials being used in all plastic application? Answer to that is the economy of scales. The cost of production for conventional polymers, polyethylene, polypropylene, is less than $1, around $1, and it's being produced 10 to the 8, so millions, hundreds of millions of tons every year. So if you look at the higher-end plastics, Teflon, copolymers, you see that the prices goes up, and the production goes down. $10 per kilogram is a range where you can produce these materials. On the other hand, bioplastics, which are natural alternative to the plastics that are synthetic plastics that are being used at a much lower production rate of millions of tons every year, but the cost is higher. when it comes to the natural silk, you can see the cost of production is $50 per kilogram, which is one of the key problems where there was alternative was needed in the a century ago. So if we try to make these materials in the lab, the common problem is scaling up. Although we can scale up these technologies, and there are different companies which are working on this, so the key problem is still the cost of production. Let's look at the final case, which is the state, the primary driver. So regulations and education are the two components that the states can play a key role here. So better design of plastics, education of the public of the single use of plastics, as well as new next generation recyclings are the key challenges here. If we can educate the public, we can increase and we can decrease and prevent plastic pollution. So as you show in the previous slides, our material can increase the lifetime of textiles, which at least contributes to the minimizing the plastic pollution. So if we can simply increase the lifetime of any textile by 3 months, as I said earlier, we can increase 5 to 10%. We can decrease the 5 to 10% of carbon footprints. So I think there is hope here which can contribute to the future generation of how we can design, how we can implement some of these new technologies into the textiles. In conclusion, I would like to summarize that we have been using natural fibers since the dawn of civilization. So new synthetic fibers came into the play for the last 100 years. So what's important is they have been causing lots of different environmental problems. So new class of materials are needed. And squid ring teeth is one of this new class of material that have the ability to increase lifetime by self-healing properties and that have unique thermoplastic properties for textile and leather applications. And I would like to also mention that the education is a key component of the plastic, preventing plastic pollution. And as you see in our university, we have the new exhibition on plastic entanglement. And these pictures is from the entrance of the museum, art museum here, which clearly shows we can educate people. Although this will be a slow shift, but it will be very important to break the culture, and we can use education and art as a tool for liberation and to learn more about these problems. In summary, I would like to acknowledge the funding agencies as well as my students and my collaborators that helped me to work on this project in the last 7 to 8 years. Thank you very much, and I will take any question that you may have.